Welcome. So today we're going to look at parabolas. So we'll start with an introduction to parabolas, and mainly we're going to focus on various ways to sketch parabolas. So we study parabolas with an equation of the form y equals x minus k squared plus c, or y equals minus x minus k squared plus c, where c and k are particular real numbers. And we're just going to start with this kind of representation of that parabola, but then we'll get into other forms of this. Note that we can use these techniques more generally, since if we expand this, expanding that square there, we have x squared minus 2kx plus k squared, and then we have the plus c, but we can put the k squared plus c into a bracket together to emphasize that that is our constant term. Now, since squares are always greater or equal to 0, and they're equal to 0 exactly when, precisely when x is equal to k, because that is what makes this 0, we see that y equals x minus k squared plus c is always greater or equal to c, and the lowest it can go is c. Y is equal to c precisely when x is k. So this means that the point k comma c is our minimum turning point in this equation of the parabola y equals x minus k all squared plus c. Similarly, the point k comma c is the maximum turning point of the parabola where we have a minus in front. Y equals minus in brackets x minus k all squared c. Okay, so let's go down and look at our picture. So here I've got a picture of a parabola with leading coefficient a positive, and so what I'm talking about here when I say this is this would be the parabola of the form y equals x minus k all squared plus c. So a is usually referred to as the leading coefficient of the parabola in expanded form. So here in this one, a would be equal. Okay, so here we see we have an axis of symmetry at x equal to k. So I'll point that out. This is the line, the vertical line, x equals k, and there's symmetry about that line in the parabola. Down here at the bottom, we have the point kc. So this is our minimum turning point. And I'll just indicate this little arrow. Okay, so now let's consider a few features of this parabola. So we've already pointed out that we have our axis of symmetry at x equals k, which occurs when x minus k is 0, and that's just a rearrangement of x minus k is 0 to obtain x equal to k, called our axis of symmetry. But here, let's notice we have a y-intercept. Now, there's always a y-intercept. There's not always x-intercept real. Okay, so let's point out we have a y-intercept when x is 0, and in this case, it's k squared plus c in this form of the equation. Okay, so we have here when x is equal to 0, we have y equals k squared plus c. So the point 0, k squared plus c is the y-intercept, which is the intersection of our parabola with the y-axis. Now, when y is equal to 0, we have x minus k squared plus c is 0. And now rearranging this, taking the c over to the right-hand side, x minus k all squared is minus c. If c is less than or equal to 0, then minus c is greater or equal to 0, so that x minus k taking square roots is plus or minus the square root of minus c. Now, in that case, that c is negative or 0, minus c will be positive or 0, and so that square root is a real number. And we have, taking the k over to the right-hand side, as in adding k to both sides, x is equal to k plus or minus the square root of minus c. Remember, what we're doing here is we're solving for x when y is 0. So that we have the point k minus the square root of minus c, comma 0, and k plus the square root of minus c, comma 0. These are our two x-intercept points. Remember, we have a plus or minus there. So these are the points of intersection with the x-axis. Okay, example 1.69. Consider the parabola shown below. Find the minimum turning point, x-intercepts and y-intercepts on the axis of symmetry. Well, I don't see a parabola shown below, so let's just draw one. Okay, something like that. I've drawn a parabola. Now, where are our x-intercepts? We have one there, we have another one there. Let's indicate those with our arrows. And then over here we have a y-intercept. Okay, down the bottom we have our turning point. In this case, we have a minimum turning point. And then we have an axis of symmetry, which is, remember, the vertical line x is equal to k when our equation is of the form y equals x minus k all squared plus c. Okay, so we've done all those, so let's move on to the next page. Sketch the parabola y equals minus in brackets x plus 4 all squared minus 6, identifying the maximum turning point, x-intercepts if they are real, the y-intercept, and the axis of symmetry. Okay, so let's begin with the axis symmetry because that occurs when what is inside the square is 0. So let's write that here. Axis of symmetry is x plus 4 is equal to 0. And so that is x is equal to minus 4, subtracting 4 from both sides. Okay, now where would that be? That would be 1, 2, 3, 4, somewhere here. So let's put in a dashed line, and I want to extend my x-axis while I'm at it. So there's our axis of symmetry. Now, when x is equal to 0, say when x is equal to 0, we have y is equal to minus 4 squared. Now the bracket is around the 4 itself. The minus is on the outside, and then minus 6. 4 squared is 16. Minus 16 minus 6 is minus 22. So this is our y-intercept. Okay, and so that would be possibly way down here. Let's just pick a point. We can change the scale of our y-axis. Chosen a scale already for our x-axis. All right, so next we need our minimum, okay, our minimum turning point. This occurs on the axis of symmetry when x is minus 4. So let's say to find no, it's going to be a maximum turning point, isn't it? Because we have a leading coefficient that is negative. So that is a maximum turning point. X is equal to minus 4. And so when x is equal to minus 4, this is 0. And so we have y is minus 6. And so point minus 4 minus 6 is our maximum turning point. Now, since we've chosen minus 22 down here, we should choose minus 6 to be somewhere up here. Okay, and so then this would be our maximum turning point. So our parabola looks something like that. Now we can see that since there is no crossing of this, because that's the maximum, no crossing with the x-axis, let's note that since the point minus 4 minus 6 is the maximum turning point, and I'll just put maximum point, the parabola does not cross the x-axis. Okay, so what does that mean? Hence, the x-intercepts are not real valued points. Okay, so I'm going to write not real points, but it just means that the coordinates, they're not real number. Okay, we would be required to take the square root of a negative number to obtain them, and so they don't show up here on the x-axis as real points. All right, let's move on to the next page. Topic: sketching parabolas using transformations of y equals x squared. So we discussed sketching parabolas of the form y equals a in brackets x minus h all squared plus k from the point of view of transformations of the parabola y equals x squared. Okay, so first of all, we have up or down translations, and that's shown there. So the first one I have in here, the middle one, that's y equals x squared. Okay, and then up here I have y equals x squared plus some positive number k. That'd be this top one. And then this one would be y equals x squared minus some positive number k. Just note k is positive in this example. Over here in the middle, we have y equals squared. Now, when we are shifting over to the right, this is somewhat counterintuitive. Remember, our axis of symmetry occurs when the inside is 0. So this would be y equals x minus h all squared, where h is a positive real number, okay, as to that curve, parabola. Now, if we're shifting the other way to the left, then we have y equals x in brackets plus h all squared for this one. Again, where h is positive. Okay, remember its axis of symmetry would then be x plus h equals 0, which is x equals minus h. And I hesitate to draw those axes of symmetry on there, but if it helps you, you draw those. All right, so next, let's consider dilations. Y equals ax squared is a dilation of y equals x squared by a. Now, if a is positive, then the parabola y equals ax squared has a minimum at the point 0, 0. and we say that the parabola is concave up. If, on the other hand, a is negative, then the parabola y equals ax squared has a maximum at 0, 0, and we say the parabola is concave down. So this one's concave up, this one is concave down. Furthermore, if the dilation has a greater than 1, then y equals x squared is stretched upwards to become y equals ax squared. So if we have the middle one being y equals x squared, then this could be something like y equals 2x squared. And then this one down here, which is our case, a between 0 and 1, it's positive but less than 1, say y equals 1/2 times x squared. Then it's compressed downwards from y squared. So it's like squashed downward. Y equals x minus h squared is a right translation of y equals x squared. So we've discussed this earlier. H units to the right. Y equals x plus h squared is a left translation of y equals x squared, h units to the left. Okay, again, we are assuming in this case that h is positive. Y equals x squared plus k is an upwards translation of y equals x squared, k units upwards, where again we're saying k is positive. Y equals x squared minus k is a downwards translation of y equals x squared, k units downwards, again k is positive. Now y equals a in brackets x plus h all squared plus k is a combination of translations and a dilation of y equals x squared. Okay, so here in this picture I've got an example where this is the curve y equals x squared, and then over here we've got y equals a in brackets x plus h all squared plus k, where the point 0, 0, it moves up k units, so the minimum, if this is the minimum, moving up k units, and if we've gone to the right here, well then h is negative in this example to make it match with this. That would be the point minus hk. Okay, and so we're shifting from this origin to this point as we transform y equals x squared into this parabola. Example 1.71. Describe the transformations that transform y equals x squared into y equals minus 2 in brackets x minus 3 squared plus 4, and sketch this parabola. Okay, so what are the translations we're doing? Well, we shift to the right. So step 1, shift right 3 units. Okay, so we go to the right 3 units. Then in step 2, multiply by a equals minus 2. Now what that does is it inverts the parabola from being concave up to concave down. Okay, and then in step 3, add 4, and hence we translate up 4 units. Okay, so that's the description of what's happened to transform y equals x squared into this parabola. Now we've got to sketch the parabola. So what is our axis of symmetry? It's x equals 3. So 1, 2, 3, 4. Okay, let's indicate our axis of symmetry. I like to use a dashed line for that. All right, so when x is equal to 3, y is equal to 4. So here we have a maximum point. All right, now also when x is equal to 0, what is the value of y? Y is equal to minus 2 in brackets minus 3 squared plus 4. Now minus 3 squared is 9, that's plus 9. 9 times minus 2 is minus 18. We have 4 minus 18, which is minus 14. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We've got our y-intercept way down there. Okay, so we can also find our x-intercepts, but that's a future lesson. So let me just open my software Mathematica to help out with this to make that quick. And I will just say expand and then factor. Okay, and so what I see there is it doesn't have any nice integer factor. Instead, I'll replace the word factor with solve equation equal to 0. Okay, and I can see that I have 2 real roots, 3 plus the square root of 2 and 3 minus the square root of 2. Now I want a numerical approximation of those so I can indicate where they are on my graph. Okay, so I have 4.41. That'd be roughly there. And then I have 1.58, around about there. Okay, which allows me to finish sketching this parabola, something like that. So I'll just put note, x-intercepts occur at x equal to approximately 1.59 or x approximately 4.41. Okay, moving on. Sketching parabolas using factorization. The sketch y equals ax squared plus bx plus c, where a is non-zero. Now note, if a were equal to 0, this would not be a quadratic, it would be linear. Okay, suppose we're able to factorize the right-hand side in the following form: px plus q times rx plus s, where p, q, r, and s are whole numbers. When y is 0, we get the x-intercepts by solving each of these linear equations, each of these equal to 0, so that, taking the q over to the right-hand side and the s over to the right-hand side, we have x is minus q over p, or x is minus s over r. We have the two x-intercept points, minus q over p, comma 0, and minus s over r, comma 0. Now, when x is equal to 0, we have y as c. Subbing in 0 there, we just have y equals c. So we have the y-intercept point 0, comma c. All right, so let's use these principles to sketch the parabola y equals x squared plus 4x minus 21 by factorization. Okay, now remember what we do when we factorize a quadratic. We want to write the divisor pairs of this constant term, but I do so with the absolute value of it. So I'll write the divisor pairs of 21 are, we've got 1 and 21, and we have 3 and 7, and that's it. Now I'm looking for which one of these, because I've got a minus 21 there, which one of these has a difference of 4. So 7 minus 3 is 4. So I know then that x squared plus 4x minus 21 has x with a 3, x with a 4. Now which signs do I put here? Or sorry, the 7. Okay, yes. Which signs do I put? Well, it comes out positive 4. So I want the larger of the two numbers to carry the positive sign there and the smaller to carry the minus sign. And then I check by expanding this. Yes, that does give me that when I expand it. Okay, so that's the factorization of that. So now we've got y equals x minus 3 times x plus 7. Okay, so when y is 0, we have x minus 3 is 0 or x plus 7 is 0. So x is equal to 3 or x is equal to minus 7. Okay, so this gives us two x-intercept points. 3, 0 and minus 7, 0 are the x-intercept. Now for the y-intercept, that's easy in this case. So when x is equal to 0, y is equal to minus 21. Just subbing in 0 there, I get minus 21. And so that gives us 0 minus 21 is the y-intercept. Okay, now to find our maximum or minimum, I know it's a minimum here because the leading coefficient is positive. So to find the minimum, I would have to complete the square here, but that's for a future lesson. All right, so we'll do this without completing the square. Let's find our two x-intercept points. We have 1, 2, 3, 0. And then we have minus 7, 0. So that'd be probably like, say, way over here. And then we have 0 minus 21. So that'd be something like way down here. And then halfway between those, we would have our axis of symmetry. Now I can just look at these. What is the average of minus 7 and 3? So if I add those two together, I have minus 4. Divide that by 2, I have minus 2. So minus 2 would be my axis of symmetry there. Okay, and then we'll just do our best to sketch a parabola that fits those parameters. Here we go. Okay, next lesson, sketching parabolas by completing the square. So if we have y equals a in brackets x minus h all squared plus k, then expanding that, we'd have a in brackets x squared minus 2hx plus h squared and then plus k. Expanding that a, distributing over this sum here, this goes with this, this goes with this, this goes with this. So we have ax squared minus 2ahx plus ah squared plus k, but I'm going to put that in brackets. All right, so this here is the b, this here is the c. If given y equals ax squared plus bx plus c, then to complete the square is to find h and k such that y equals ax squared plus bx plus c is a in brackets x minus h all squared plus k. All right, so we want to solve for h and for k here. So we've got b from our expansion is minus 2ah and c is ah squared plus k. So if I take this first one and solve that for h, then I'm dividing by minus 2a. So I have b over minus 2a. And then if I take this and solve for k, I have k is equal to c minus a h squared, where h is this. And so I can sub in the value that I got in terms of a and b. So I've got c minus a in brackets b squared over 4a squared when I square this. Okay, and so I can simplify that by putting it all over 4a squared, or all over 4a, because we can do a cancellation of one of the a's here. So this is c minus b squared over 4a, which is multiplying the top and bottom of the c by 4a. To get a common denominator, we have 4ac minus b squared all over 4a. Okay, and that is our k. All right, so we've got some formulas for completing the square, but that's not usually the way that I complete the square. I don't use formulas because, hey, I don't love to remember loads of things when I can reconstruct them easily. Okay, so the first one says complete the square using the formulas for h and k, but in the subsequent example, I'm just going to do it the way I usually do it. Okay, so in this example, we have a is 2, b is 10, and c is minus 48. Okay, and so let's first find h. H is b over minus 2a. So using our formula here and the a, b, and c values that we have, this is 10 over minus 2 times 2. And so that's minus, simplifying our fraction, 5 over 2. 10 over 4 is 5 over 2. So we have minus 5 over 2 for h. Okay, now if I just take this and my h value, I can get k. So k is c minus a h squared, which is, c is minus 48. So minus 48 minus 2 times, in brackets, minus 5 over 2 squared. Okay, so simplifying this, minus 48 minus 2 times 25 over 4. Now we can cancel the common 2. Since this is going to be all over 2, I want that minus 48 to be over 2 as well. So twice 48 is 96. So minus 96 over 2. And then this is minus 25 over 2. All right, now I want to add 96 to 25. So 96 plus 25 is 121. So for this, I get minus 121 over 2, and that's our k value. Okay, so coming back to this, we have y is equal to 2 in brackets x minus 5 over 2 squared minus 121 over 2. Okay, now I would want to simplify this. So that's 2 in brackets x plus 5 over 2 squared minus 121 over 2. And that's the square. Okay, next page. Now we've got the same equation. Yep, the same equation there. So complete the square without using forms. Okay, so I'll show you what I normally do here. So I'll write y equals, and I'll first factorize the leading coefficient out of everything. And it might leave fractions when I do that, but in this case it doesn't. So 2 in brackets x squared plus 5x minus 24. And that's my first. Okay, so my next step following that is I look at coefficient, or the number next to the single x, x to the 1, coefficient of x, that's 5 here, and I divide that by 2. Let's note half of 5 is 5 over 2. Does that look familiar? It should. And so what I do is I pack that into brackets with a square. But it's not going to be totally true here in agreement with this, because if I were to expand this, I would have x squared plus 5x, and then I'd have plus 25 over 4, right? Because the square of 5 over 2 is 25 over 4. Now that wasn't there in this version, so I need that to make that go away. So I subtract, okay, I'll put it in as it was, 5 over 2 squared, and I still have the minus 24. Okay, now all I have to do is tidy this up and simplify it. 2 in brackets, x plus 5 over 2 squared. Then we have minus 25 over 4 minus 24. Okay, 24 times 4 is 80 plus 16, which is 96. So that's 96 over 4. 96 plus 25 is 121. And then finally, you might want to distribute, expanding that 2, distributing it over the difference. And so we will get 2 x plus 5 over 2 all squared minus 121 over 2. So 2 over 4 is a half. Okay, and this is what we got earlier using formulas, but here you see we didn't have to use formulas, and hence we didn't have to remember formula, which I think is better. Okay, next, use the completed square, what we have here, to sketch the parabola. So what this version tells us is it tells us an axis of symmetry and a minimum or a maximum point, depending on the sign of the leading. Now, the sign of the leading coefficient 2 positive, right? So we have concave up, and hence we have a minimum. So let's say since 2 is positive, we have concave up. And so the point obtained by getting 0 here, which is the point minus 5 over 2, comma. Now, when that's 0 there, we have minus 121 over 2. This is a minimum turning point. And that's one of the main values of completing the square, is to be able to find this minimum turning point. All right, but we have some other skills too, like factorization. So factorizing 2x squared plus 10x minus 48. We can pull the 2 out as we did earlier. Now, what are the divisors of 24 that have a difference of 5? Can we think of any? How about 8 and 3? 2 in brackets x, put the 3, and then I'll put an x and an 8, and then let's decide the sign. Now, I want the sum to come out positive, so the larger of the two divisors should carry the positive sign inside the bracket, and the smaller of the two should carry the negative sign, so that when they add together, I get plus 5. In other words, 8x minus 3x gives 5x. And note the product gives minus 24. So that's good. I factorized that. So what does that give us? It gives us 2x intercept point. So 3, 0 and minus 8, 0 are the x intercept. Okay, can we also get a y-intercept? Well, yes, we can when we put in x is 0 into this, right? Because this is our y. We get 2 times minus 24, which is minus 48. So 0, comma, minus 48 is the y-intercept point. Okay, so all of that information together with the axis of symmetry, so x equal to minus 5 over 2 is the axis of symmetry. All of that information is enough for us to be able to sketch this. Now 5 over 2 is 2.5, 2.5. So 1, 2, 3, 4. Here we have an x-intercept point. 1, 2, 3, 4, 5, 6, 7, 8. Another x-intercept point. Half of 121 is 60.5. So our minimum turning point would be way down here. Okay, now let's put in our axis of symmetry. So minus 2.5. So that would be somewhere in here. And then our y-intercept minus 48. So let's just say, suppose that's there. And then it looks like our minimum could be here, where this is minus 60.5 or minus 121 over 2. Okay, so let's finish off the sketch. And there's our parabola. Okay, sketching parabolas using formulas. So here I'm going to derive what's called the quadratic formula. So remember, first, in my process of completing the square, I factored out the leading coefficient a. So what I would have remaining in the brackets is x squared plus b over a times x plus c over a. And now that's fine because a is non-zero, because if a were 0, this would be linear, and we've assumed that it's not just linear. So we assume a is not equal to 0 here. Okay, now our next step, remember we look at the coefficient of x inside the brackets and we divide that by 2. I'm going to note half of b over a is b over 2a. Okay, and remember what I do with that, I pack that into a square. X plus b over 2a, and that's all squared. And so if I were to expand this, I would get x squared plus b on a times x plus b squared over 4a squared. So I need that b squared over 4a squared to go away, and I do that or achieve that by subtracting b squared over 4a squared. I still have the plus c over a. Okay, now what remains here is to tidy this up in order to complete the square. So I want to put this c over a over 4a squared instead, and so I need to multiply top and bottom by 4a. So 4ac over 4a squared, and then we want to bring this over a common denominator of 4a squared. But I also want to pull out a minus sign out of this while I'm at it. Put minus in brackets b squared minus 4ac all over 4a squared. Okay, and then we can, if we want to, expand distributing that a over the difference. And so when we do that, we have a x plus b over 2a all squared, and then minus b squared minus 4ac over 4a. Right? Because a divided by a squared is a, 1 over a. All right, now if y were equal to 0, then I could take this line, divide throughout by a, and get x plus b over 2a all squared is equal to b squared minus 4ac over 4a squared. And then taking square roots, x plus b over a is equal to, when you take square roots and you're solving, you get plus or minus. So the square root of b squared minus 4ac all over 4a squared. That square root extends over the entire fraction. All right, now let's simplify this square root. We've got plus or minus the square root of b squared minus 4ac. The square root of 4a squared is 2a, okay, and that's x plus b over a. So the last thing I need to do in order to solve for x is to subtract, should be 2a, subtract b over 2a from both sides. And so x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And this is called the quadratic formula. All right. So moving on, there's some key information in there. Let delta be b squared minus 4ac. Now that's called the discriminant of the quadratic polynomial ax squared plus bx plus c. And we come to an important result now. Let delta be the discriminant, so that character is called delta, of ax squared plus bx plus c, which I've called f of x. If delta is positive, then f of x has two distinct real roots. And that means that the sketch of the parabola crosses the x-axis, like what we see here and here, when delta is positive. If, on the other hand, delta is equal to 0, then f of x has one distinct real root. In fact, it's a repeated root in the quadratics of the form f of x is a in brackets x minus h all squared. So that touches the x-axis at a tangent, a single tangent point. But because that's in a square, I call that a repeated root. So x equals h is a root of this twice. If delta is negative, then f of x has no real roots, but there are two non-real roots, complex. That means that the sketch of the parabola is either above or below the x-axis entirely, like what we see in these two pictures. So this is concave up, so when a is positive, this is when a is negative. So all of these in the top row have a positive, and all of these in the bottom row have a negative, like so. Okay, continuing. From that, we have the vertical line x equals minus b over 2a is the symmetry like what you see there. And the point minus b over 2a comma minus delta over 4a is a formula for the turning point. If a is positive, then that should say minimum, right? Minimum, and the parabola is concave up. If a is negative, then that's a maximum, and the parabola is concave down. The y-intercept point is 0, c. If delta is greater or equal to 0, then the x-intercept point or points is or are these 2 points. So we have formulas for x-intercept points. Okay, so let's have a look at example 1.76. Sketch the parabola y equals 3x, that should be squared, minus 18x minus 48 using the above formula. All right, so my first step, I want to factor the 3 out of everything if I were to complete the square, but I'm going to use formulas to do this. So I'll put a is equal to 3. I'll put b is equal to minus 18. I'll put c is equal to minus 48. Okay, now I want to calculate the discriminant. So delta is b squared minus 4ac. And so that's minus 18 squared minus 4 times 3 times minus 48. Okay, I'll get my machine to do this. You can use your calculator if you want. And so I get 900 for the discriminant. Now, notably, it's positive, so I expect two distinct real roots. So 2 crosses of the x-axis. All right, so now let's use the formula for the axis of symmetry. And so that's x equal to minus b over 2a. And in this case, minus b is plus 18, so that's 18 over 2 times 3, 6. And so our axis of symmetry is x is equal to 3. Okay, and now let's find our minimum. We have x is 3. This occurs on the axis of symmetry. And then the y value is minus delta, which is minus 900 over 4 by a. Okay, and now let's simplify this. 900 divided by 3 is 300. 300 divided by 4 is 75. We have the minimum point 3 comma minus 75. Okay, now let's use these two formulas for our x-intercepts. So x-intercepts, we have minus b plus or minus the square root of delta all over 2a, and that is minus 18 is plus 18 plus or minus the square root of 900 all over 2 times 3, which is 6. Okay, the square root of 900 is 30. So we have 18 plus or minus 30 all over 6. So 18 plus 30 is 48. 48 over 6 is 8. Now, if we have a minus there, we have 18 minus 30 is minus 12. Minus 12 over 6 is minus 2. Okay. So let me just double check via factorization. So pull the 3, common 3 out, 3x squared minus 6x minus 16. Okay, and then 16 is 2 times 8, 3x with a 2 and x with an 8. Okay, so next, the coefficient of x is negative, so we want the larger of these two to carry the minus sign and the smaller to carry the plus sign. Okay, now does that agree with these two? Yes, it does. Okay, and so we have x-intercept points minus 2, 0, and 8, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9. At that x-intercept point, and then the other one occurs when x is minus 2 here. Okay, now our minimum occurs when x is 3. So we also have our axis of symmetry when x is 3. And then let's put on here minus 75. Something like that. Now, do we have a y-intercept? Yes, that occurs when y is minus 48. Somewhere, say here, and then we can now finish sketch like so. Okay, applications of parabolas. A stone is tossed vertically upwards 15 meters per second and accelerates downwards due to gravity at 10 meters per second so that u is 15, a is minus 10. Let y be the height of the stone after t seconds. If the height y is given by this formula, y equals ut plus a half at squared, find the maximum height of the stone and sketch the parabola relating y to t. Okay, so we have y equal 15 plus 1/2 times minus 10 times t squared. So this is 15 minus 5 t squared. This is y. So this describes the height or elevation of the stone after t seconds. Let's note that this is the height of the stone after t seconds. Okay, so we're asked here to use our skills to sketch this. So that should be 15t. We've forgotten the t there. Okay, so I might first want to factorize this. So factorizing y is equal to, now I can see I can pull out a common 5t. 5t, now it remains inside the bracket 3 minus t squared. So that if, no square there, because when we expand this, we get a t squared. Okay, so 5t outside of 3 minus t. If we were to expand that, we would get 15t minus 5t squared matching that. Okay, good. So what this tells us is two x-intercept points, but in this case, they're t-intercept points. So two t-intercept points, t equals 0, and so that is 0, 0, and 3, 0. Okay, so let's come down here and note these on our graph. We've got 0, 0, then we have 1, 2, 3, 4, 3, 0 there. Okay, so to find the maximum, we want to complete the square here. So to find the maximum point, we complete the square. All right, so we have y equals minus 5t squared plus 15t. I want to pull out the minus 5. We have t squared plus 3t. Now remember what I do. I look at the coefficient of the x to the 1, but in this case it's t to the 1. I divide it by 2 and I pack that into a square. Minus 5 side of in brackets t plus 3 over 2 all squared. And then I subtract the 3 over 2 all squared. So that would be subtracting 9 over 4. Now, we don't have a constant term inside the bracket, so I can close that brackets now. All right, so the square is completed. I could, if I want to, expand the -5, distributing it over that difference if I want. So let's do that too. Y equals -5 in brackets t plus 3 over 2 all squared. And then that's plus 9 times 5 is 45 over 4. Okay, so this gives us our maximum, which occurs. No, that should be a minus here, right? That should be a minus. That should be a minus. That should be a minus in there too. Okay, so maximum occurs when t is equal to 3 over 2 seconds, right? So that's the second and a half. And y is equal to 45 over 4, which is 10 and a quarter. So 10.25 meters. Okay, so our axis of symmetry is half of 3, which is 1.5. Maximum here is 10.25 meters, and I just need to draw a parabola. Okay, now since the t-axis is the ground, I won't draw it below that. So that's the bottom there. Okay, so now to answer the question, find the maximum height of the stone. Well, the maximum height of the stone is 10.25 meters. Okay. A gardener wants to erect a rectangular fenced area using 50 meters of fencing. That's the length of the fencing. Determine the dimensions that give maximum area to the fenced region. Okay, so let the dimensions be x meters wide and y meters long, so that a is equal to x times y. Okay, now in the sentence here, we read, and it helps to have a picture of this. We have y there, we have x here, we have x here, we have y here. So we read that the perimeter here, so in other words, x plus y, which is 2x plus 2y, that's 50. Okay, so dividing throughout by 2, we get x plus y is 25. Okay, now I want to solve for y. So y is equal to 25 minus x, and then substitute that back into my equation for the area. A is equal to x in brackets 25 minus x, and if I were to expand that, I'd have 25x minus x squared, which has a leading coefficient -1, and so this is concave down. So we have a maximum. Okay, and so my intercept points here, x-intercepts 0, 0, and 25, 0. Okay, now y-intercept is 0, 0. How about the maximum? Okay, so for the maximum, I would want to complete the square. To find the maximum, we complete the square. Okay, now again, what I like to do is factor out the leading coefficient, putting a equals minus in brackets x squared minus 25x. Then I take half of the coefficient of x, pack that into a square, so x minus 25 over 2 all squared, and then we subtract the square of this minus 25 over 2. Now 25 squared is 625, 625 over 4. Okay, and then expand the minus back out. Okay, and so the maximum occurs when this is 0. So we have x comma a is equal to 25 over 2 comma 625 over 4. Now if x is equal to 25 over 2, what's the value of y? Well, y would be equal to 25 minus 25 over 2, which is 25 over 2. And if we do that division, half of 25 is 12.5 meters. So the maximum area is a quarter of 625, just calculate, which is 156.25 square meters when x and y are equal to 12.5 meters.